Let's get started. Good afternoon from Beijing, and also good morning / afternoon / evening for everyone joining us from places over the world. This is the APAC DNS Forum 2024 pre-event webinar, Evolving Operations, Abuse, and Security of the DNS. And my name is Chaoyu Lu. I am a postdoc at Tsinghua University, and I'll be your moderator for today. So going straight to our topic, the DNS has remarkably endured for over 40 years as a cornerstone of the internet. And especially in recent years, we've seen not only the vast development of DNS-based functionalities and extensions, but also new security problems and evolving abuse methods. And so in today's session, we're very glad to have 5 speakers with us who will be sharing their exciting research efforts. And spoiler alert, our speakers will bring in discussions from more classic DNS features, such as public suffix lists and DNS glue, to more recent additions like DNS error reporting, encryption, and even one crossing with ChatGPT. So very interesting things to expect ahead. And before we start, special thanks to Qi-Anxin Group, Alibaba Cloud, China Academy of Information and Communications Technology, and the InForSec Forum for leading this session. And we also appreciate folks at ICANN for their tremendous support in organizing this webinar. And finally, for our remote participants over Zoom, if you've got any questions to the speakers, please type them anytime into the chat box of Zoom. And after each talk, we'll have about 2 minutes for questions, and the moderator will ask them for you. Okay, so that's it from me. And now to our first speaker, Mr. Stephen McQuiston, joining us from remote. And Stephen is an assistant professor at the University of St. Andrews. He works on projects looking into improve the Internet Protocol standardization process and its outputs by designing tools and interventions that address both technical and social challenges. He will talk about a first look at the privacy harms of the public suffix list based on their research work accepted to the IMC Conference 2023. And now I'll give the floor to Stephen. Stephen, please.
Yes, so thank you for that introduction. So the work that I'm going to present today, as Chao Yi said, was a paper that was presented at the Internet Measurement Conference last year. And that was work with colleagues at Brave, University of Glasgow, Imperial College, and HKUST. Now, this work is looking at a piece of infrastructure called the public suffix list. Now, the public suffix list tries to solve the problem of determining domain boundaries on the web. So that essentially boils down to the question of how do we know when 2 domain names are related to each other? Now, the framing of the paper is around about privacy on the web. So we want to answer this question of whether 2 domain names are related to each other so that software like web browsers, for example, knows when to share data. So, for example, you can imagine navigating to google.com and signing in. If you then go to something like scholar.google.com, you can imagine that you'd want to be signed in there as well. Now, we want our browser to share the cookies and other data that is necessary to enable that functionality. We essentially want it to sort of do the right thing, to do the thing that is best for usability. Now, of course, we can see that these are 2 different domain names, scholar.google.com and google.com. But the terminology here is that these are part of the same site. They're both owned and operated by Google. And so the privacy boundary that we want to construct here is around google.com. And we want to enable our browser to share data across different domain names that are essentially part of that same google.com site. Now, the obvious sort of counterexample to this is that if I then navigate to something like amazon.com, that is a totally different site. And we, of course, want our browser to not share data, to not share cookies set at google.com with amazon.com. So that's essentially the question and the problem that we're trying to solve. Which domain names belong to which site? That's essentially the question we want to answer. Now, of course, we can see from the example that I've just given, we can think that there might be a sort of trivial way. We might have a rule that we could apply here to determine which domain names belong to which site. So we might come up with a rule. We could say that maybe the first name immediately before the last dot in the domain name. So if we highlight that here, perhaps that indicates which site a domain name is part of. And for this example, that rule works. So we can see google.com and scholar.google.com are both Google, and then amazon.com is obviously Amazon. But then, of course, we've got other TLDs. So if I add in bbc.co.uk and apply that same rule, then we might think that the site here is CO. Of course, that's not the case. And with this rule, then we would construct the privacy boundary around every single .co.uk website. When in actual reality, the site here is BBC, for example. Okay, then, so we can't come up with that rule, but perhaps then we just use the sort of ICANN list of TLDs, and we use that to determine the site boundaries. But of course, we've got sort of private companies, private services that allow users to register names. So for example, if I go to blogspot.com, that service allows me to register sort of my own blogspot.com subdomain. I could have stephen.blogspot.com, but stephen.blogspot.com is owned and operated by me, but example.blogspot.com is perhaps operated by someone totally different. And again, we would want our browser to keep those sites separate. So we wouldn't want to share cookies between the different subdomains of blogspot.com. So for example, here, the site then is example. And so if we work through all of this, we can determine then that there's really no heuristic, there's no rule that we can apply in order to determine whether two domain names are related to each other. And so we have to essentially come up with a different approach. Now, the approach that we've taken for the web is essentially to construct a list of the possible suffixes that users can register names under. So here the list would be com, co.uk, and blogspot.com, because you can register a name under that suffix. Now, the list of these suffixes is known as the public suffix list. The public suffix list looks a little bit like this. It's essentially just a plain text file of all of the suffixes under which users can come along and register names. It's a sort of community-maintained project that was started by the Mozilla Foundation in early 2007. And it includes all of the ICANN TLDs, as you can see in the example on the left, but it also includes sort of private suffixes like blogspot.com from the previous example, where sort of companies or other organizations allow users to register names. Now, if we think about the sort of growth of the list over time, it looks a bit like this. We can see, again, it started in sort of early 2007. There was some sort of rapid early growth in the size of the list, and that sort of stabilized over the last few years. But there's around about 10,000 entries on the public suffix list. Now, sort of owing to the time constraints, I'm not going to go into the sort of details of what the suffix list looks like. Those details are all in the paper. Okay, so we know now then about the public suffix list. One of the questions then that we want to answer in the paper is how can that list then be misused? Now, to sort of think about this, we're going to work through a very brief example. So we'll go back to that sort of example set of suffixes. So this green box here represents my copy of the suffix list. Again, in reality, it's a much larger list. It has about 10,000 entries. So this is just a trivial example. And then we'll imagine that we've got a web browser and the user has made requests to this set of domain names on the left-hand side of the slide. And the web browser then is going to process that set of requests using its copy of the public suffix list. And we can see then that it constructs privacy boundaries around these sites. So it does exactly what we'd expect. Example.co.uk has its own site, and then each of good.blogspot.com and bad.blogspot.com are within their own site as well. So no cookies are being shared across these different domain names. They're each contained within their own site. There's no data sharing. However, if we think about what might happen if we had an old version of the suffix list, so let's say we had a version of the suffix list that didn't have blogspot.com on it. Now, this time, when my browser sees this set of requests, it's then going to construct this set of sites. And we can see that example.co.uk works as before, but this time, because blogspot.com is no longer on the suffix list, I'm using out-of-date old version of the list, we can see that we actually construct privacy boundaries that bring good.blogspot.com and bad.blogspot.com into the same site boundary. And so my browser then is going to share cookies and other data between these two domain names. And again, these two domain names are under different administrative control, right? So two different people own and operate those websites. And so we don't want data sharing to happen between them. We don't want cookies and other data to be shared. But because I'm using an out-of-date version of the suffix list, my browser doesn't know to construct the correct privacy boundaries between these two sites. Now, the final question that I'm going to try and answer in this brief presentation is whether or not there are actually projects out there that are using out-of-date versions of the suffix list. Now, to try and answer that, we used a tool called SourceGraph. SourceGraph lets us look at all of the GitHub repositories, all of the public GitHub repositories, and look for files inside of those repositories. And essentially, we looked for projects that had a copy of this plain text public suffix list. We found 273 projects in total. We then categorized those projects based on how they made use of the public suffix list. So we had three categories. Fixed. Fixed essentially means that the project had a copy of the list and it didn't have any code or any mechanism for updating that copy of the list. So it was a fixed static copy of the list. Updated means that the project contained the list, but there was also code to perhaps fetch the list routinely. So to get a new version of it, to try and prevent using a stale or out-of-date copy of the list. And then finally, this third category is dependency. And that basically just means that the project has a third-party library that makes use of the list. Now, we manually went through each of these repositories, each of the 273, and then labeled it based on how it was using the public suffix list. We found that of the 273 projects that we labeled, that 68 of them were making use of a hard-coded fixed version of the public suffix list. And as we saw previously, that means then that as the public suffix list gets updated, that these projects then are potentially opening up users to privacy harms. They're maybe not constructing the site boundaries in the right way, as we saw in the example. And of that 68, we found that 43 of them were using out-of-date lists in live production code. So some of these fixed uses were in test code, so that's less problematic, but there was a significant portion, 43, where the usage was in live production code. And that included projects like password managers and things that are privacy sensitive, where we wouldn't want the incorrect boundaries to be constructed. Now, very briefly, as the sort of final result from the paper that I want to present, you can look at how old those lists are. Now, we found that the median age for the lists used by all projects was about 871 days. That's over 2 years. And again, if we think back to that example that I showed earlier, that opens up users to potentially significant privacy harms, right? If projects are using a list that's more than 2 years out of date, that means that they're missing all of the suffixes that have been added to the list in that 2-year window, and potentially then inappropriate data sharing happens across those missing suffixes. Now, the final question that the paper tries to dig into is around about whether this misuse of the list actually results in privacy harms. I don't have time to present those results in this talk, but if you are interested in thinking about the potential privacy harms, then I'd encourage you to read the paper to see those results. So just to wrap up then, we explored something called the public suffix list, which lists all of the names under which users can register their own domains. And we found that a quarter of the projects that we identified used hard-coded, outdated versions of list, and that could lead to potential privacy harms. Now, the projects that we found included security-focused projects like Bitwarden and Autopsy, where these privacy harms are fairly meaningful. And the question then that we're building towards, and that sort of gets to the topic of this webinar, is, are there alternative ways of expressing domain boundaries, of answering this question of whether two domains relate to each other, are there alternative ways that perhaps eliminate some of the challenges of the public suffix list? And in particular then, could we use the DNS, perhaps with a new record type, to express some of the same information that the public suffix list expresses, and therefore eliminate some of its challenges and some of the privacy harms that identified? Again, this was work from the Internet Measurement Conference, and I've popped the link to the paper at the bottom of this slide, and I'd encourage you to read it if you're interested in this topic. But with that, thank you very much, and I'm happy to take any questions. Thank you.
Okay, thank you, Stephen. Do we have any questions from our audiences? One quick question from myself. I noticed that I think it's page 33 or 34, there is a graph, and the repositories are categorized as fixed, updated, and dependencies. So what does dependency mean?
So in this context, dependency means that a project has maybe a third-party library that is making use of the suffix list, and we keep those labeled as one type. We don't want to attribute the sort of third-party library to the project itself, so we label it as dependent. Okay,
so when analyzing these projects, you're actually analyzing the projects that are dependent on by these projects. Is that correct?
Yes.
Okay. Okay, thank you. Any other questions?
Thanks.
Okay, so in that case, thank you, Stephen, and we'll move on to the next speaker. Our next speaker also comes from remote, Mr. Yevgenia Nosik, a PhD student at University Grenoble-Alpes. Yevgenia does research on DNS, network measurements, and cybersecurity to build a safer internet for everyone. And her talk today is about extended DNS eras, unlocking the full potential of DNS troubleshooting, also based on her recent paper accepted to IMC Conference 2023. And she is also awarded by the IRTF Applied Networking Research Prize 2024 for this interesting work. And Yevgenia, whenever you're ready.
Thank you very much for the introduction. So yes, today I'm going to talk about extended DNS errors. So we all know that DNS is one of the most critical components of the internet because there are quite a few activities that rely on translating human-readable domain names to IP addresses or the other way around. But despite it being that critical, many things can go wrong and will go wrong. So even in this very simplest setup that they have, everything can go wrong. So one thing we can imagine is that there is some problem with the zone file. For example, it has some syntactic errors, or there are expired DNS signatures or something else. Another problem could be the software that is accepting requests whether from the end user or from the resolver, and the software is unable to do it. And then even if for once it is not DNS, it is a problem, we can experience some network disruptions. So of course, when DNS was designed 40 years ago, it was clear that things could go wrong. So we had this response code field from the very beginning. But there are some problems here. So for example, this response code 9 has two different meanings depending on whether the response contains the TSIG record, and if yes, what's its error field. Second problem is that we have this response code of 16, which was assigned twice by mistake. Okay. But then finally, if you're used to dealing with DNS on a daily basis, you probably see this server file pretty much all the time. And in this case, it gives you absolutely no information as to what exactly happened, what was wrong. So to address this very specific problem, 4 years ago, a new proposed standard was introduced, which is called extended DNS errors. So let's start with this very brief example where I have a domain name that I misconfigured so that all the DNSSEC signatures are expired. So traditionally, if we query a validating DNS resolver, we would get a serve fail. Once again, something went wrong, we have no idea what. Now, if we add extended DNS errors here, you can see that this it gives you exactly the reason what happened. So in this case, it tells you that the signatures has expired. It even gives you the ID of the DNS key that generated such signatures and the expiration field. So as for now, we have 30 different extended DNS error codes. 25 of them were introduced in the RFC from the very beginning 4 years ago, and 5 of them were subsequently added later. So they cover different aspects of DNS, so not only zone misconfigurations, but maybe some resolver policies, caching, software operation, and many others. So one thing we wanted to analyze in our paper is that how is the standard actually implemented by software vendors and public resolver providers? So these are the tests from July 2024. We tested 9 different systems. We took 4 major open source DNS software and then 5 big public resolver providers. So 9 systems in total. Then as for test cases, what we did was to create 63 different subdomains, which were either incorrectly configured, so misconfigured, or they represent some corner cases, for example, using some interesting DNSSEC algorithms, like the very new or some of the oldest ones. So I will not detail all the test cases here, but you can find them on the website. And then the methodology itself is very simple, because to each tested system we send a DNS request, and then when analyzing the response, we check whether there was an ED returned and which one. So the results were inconsistent in the great majority of cases, and identified 3 primary reasons why it was the case. So the first one is that not all the extended error codes are implemented by all the software vendors or public resolvers. So for example, none of the EDs supported by bind are supposed to detect zone misconfigurations, which was the core of our test cases. Now, the second thing is that some systems return more specific errors, while others less specific. So for example, we have this ED6 DNSSEC bogus, which can cover pretty much all the DNSSEC validation problems. But at the same time, some of the systems could go more specific and say signature expired or DNS key missing. And then the third one is that extended error codes, they may also reflect different resolver capabilities. So for example, Cloudflare resolver does not support this ED448 DNSSEC signing algorithm, so it returns the ED code 1, saying exactly that, unsupported DNS key algorithm, which does not really mean that there is some problem with the domain name itself. It's just that the resolver is not capable of handling this type of domain. Some of the cases were pretty extreme. So for example, here we have a domain name where the name servers are configured not to respond to queries. So basically, you send the request to the name server, it responds with refuse. And we saw as many as 5 different EDs returned by those 9 tested systems. So moving on to the second research question, we were wondering whether we can use extended DNS errors to find misconfigurations in the wild and on a large scale. So the methodology is here is still the same. We send 1 DNS request to analyze the response. But this time what we did was to test almost 300 million registered domain names registered as of July 2024. And then once again, we analyze the ED returned, if any. So in total, out of those 300 million tested domain names, slightly more than 19 million triggered at least 1 extended DNS error code. So in total, we had 19 unique EDs. But actually, in the great majority of cases, we did not get just one extended error, but a combination of those. So in total, we had 215 different combinations of extended DNS errors. So if we were to summarize those results, there are two biggest problems. One of those is lane delegations, when name servers are not reachable. So for example, in this case, we see that one name server refused to answer a request from Cloudflare, but we still got no error because there were some other name servers with domain names that were still functioning. However, in this second case, we got no reachable authority because none of the name servers was able to provide the response to Cloudflare. So then the second problem was DNSSEC failures. And here we could see pretty much all the existing DNSSEC extended DNS errors. So just to clarify the first two, they once again signal the capabilities of Cloudflare. It does not recognize those algorithms, so it supplied the extended DNS errors in response. So it does not mean that those particular domain names were not correctly configured. So this is one of the examples here where we get no error, but Cloudflare says that it does not support the algorithm used for signing. Yeah, and this is an example where Cloudflare would serve fail because of the DNSSEC error. It's because once again, we have expired signatures. Now, in this last example, the name is slightly misleading because even if it says the DNS key is missing, what it actually means is that there is no DNS key that would match the DS record as a parent. So that's why we get this kind of error and serve fail because validation failed. So we had this very interesting case because we had a bunch of domain names with RSig missing, but the status was the R code was no error. So that's slightly misleading because we would expect that the DNSSEC validation would fail in this case. So we see here that there is a key of a particular ID 1253 that is causing the problem. And if we go to DNSVs and we visualize this key, it actually appears that this is a standby key. So this key is not actively used to sign the zone, but it is there in case an emergency key rollover is needed. So in this case, Cloudflare was right to say that no signatures provided by this key were available, but this key is not supposed to provide any signatures in this context. So we did contact Cloudflare to ask whether it was expected to see the combination of no error and RSig missing. They told us yes, but they also updated their online documentation to clearly say that if we get RSig missing, it could be key rollover in progress, among other reasons for this extended DNS error. So to summarize, we saw that extended DNS errors are supported by major software and public resolvers, and they do help us to identify the root causes of DNS issues, although with different levels of specificity. And it is also very efficient to look for misconfigurations at scale. And overall, we believe it's a very promising technique for DNS troubleshooting. So thank you for the attention, and if you have any questions, I'm happy to take them.
Okay, thank you. A very interesting work. We have a question online. So how much impact in terms of security do these extended errors lead to regarding revealing possibly sensitive information to bad actors who query the DNS? So
yes, extended DNS errors are there. The question is who is looking at them and whether anyone is looking at them, right? Yes, if you're a bad actor, you're looking for some, you know that there is some problem with a DNSSEC algorithm. Now it's trivial for you to find those domain names that are vulnerable. Now there is some follow-up work. Actually, it's a recently accepted standard at IETF. It's called extended error reporting. So the idea is that when the resolver that supports extended DNS errors notices that there is this error, it will send a specific DNS query to the name server to report that it detected the problem. So then it's up to the DNS administrator, to the name server administrator, to act upon those reports and to fix the problem.
Okay, thank you. Because of the time limit, we will need to move on to the next speaker. Thank you, Yevgenia.
Thank you.
Now to speakers on site, we have Ms. Chendi Ma from China Academy of Information and Communications Technology. Her talk today focuses on development and practices of encrypted DNS technologies, which is a major update to the DNS that has attracted broad attention. And now I'll hand the stage over to Ms. Ma.
Okay, today the subject I'm here to present to you is development and practices of encrypted DNS technologies. Accessing DNS is the basis for people to access websites. Recursive DNS is the first step for users to access DNS. The traffic between users and the recursive DNS contains the most comprehensive and original information, which schedules the user's network access behavior. Since the DNS protocol specifies that packets are transmitted in the form of clear text, the network communication between the users and the recursive DNS is an easy target for hackers to eavesdrop on data and purse hijacking. In RFC 7626, the IETF mentioned that the best place to trap is clearly between the stub resolvers and the recursive DNS. In addition, the National Security Agency of the United States obtained intelligence of many countries, including China, through secret collection of recursive DNS data. In order to resolve the security risks caused by the plain text transmission between users and recursion DNS, multiple types of encrypted DNS, such as DOH and DOT, have been launched and have been supported and promoted by Google, Mozilla, Tencent, Alibaba, etc. Well, encrypted DNS also brings challenges for government and enterprises. Using DNS packets in plain text, security devices can detect and block network risks in time. Besides, encrypted DNS bypasses security devices, and ISP DNS needs to cooperate with the government to carry out policy regulation. However, most ISPs do not provide encrypted DNS services, so encrypted DNS bypasses the government's regulation of DNS traffic. To this end, government organizations such as the United States and the European Union have issued relevant documents focusing on requirements and suggestions for governments and enterprises to use encrypted DNS. The Russia government even issued a document banning encrypted DNS. Encrypted DNS brings both security and challenges. This sharing aims to analyze its application from 5 aspects: number, traffic, product, enterprise, and government. In the term of number, it can be seen from the figure that the number of servers of DOH and DOT has exceeded 20,000 for existing other types of encrypted DNS. As the QUIC protocol gained popularity, the number of DOQ servers, though small, grew rapidly with an annual growth rate of 46%. However, there's still a huge gap between the number of encrypted DNS servers and the millions of DO-File3 servers. In terms of traffic, from a point of view, from an international perspective, we use data from Cloudflare, the second large global public DNS in the market, as an example for analysis. In 2023, DO53 traffic will account for about 80%, and the sum of DOH and DOT traffic will account for about 20%. From the domestic point of view, according to the data provided by Baidu, Ali, and other enterprises, in 2023, the amount of encrypted DNS resolutions accounted for only 0.39%, and the amount of resolution requests was 950,000 times per second. In conclusion, there is still a big gap between encrypted DNS and DO53, and the application of encrypted DNS in China is far lower than the international level. In terms of products, we analyze all kinds of major products involved in domain name resolution between users and recursive DNS. The first is the mobile application, which mainly uses the HTTP protocol. HTTP DNS was first proposed by Tencent in 2014, mainly in China. Almost all common used apps support HTTP DNS, involving online shopping, communication, navigating, entertainment, etc. Browsers, because they natively support HTTPS, support DOH. DOH is currently supported in Chrome, Edge, Firefox, etc. These browsers have a combined market share of about 65% in China. In terms of operating system, the operating system of personal computers, servers, and mobile phones have all supported one or more types of encrypted DNS. Routers, currently only two brands, TP-Link and ASUS, support encrypted DNS. In home routers, the market share of the two brands is about 30%. In terms of recursive DNS software, the top three most used recursive DNS software in China are Bind, Pasadis, and Windows DNS, among which Bind and Windows DNS support encrypted DNS, accounting for about 48%. To sum up, the mainstream products that resolve the fault chain between users and recursive DNS have basically supported encrypted DNS. For enterprises, encrypted DNS as a new technology can attract more users. Research and the development of new technologies can also enhance the competitiveness and enterprises. So it has been strongly supported and promoted. For SP, recursive DNS is only a basic server to provide users with network access service, which is provided for free. Supporting encrypted DNS only increases its operational costs. In addition, the ISP can't directly sense the domain name resolution traffic after user use encrypted DNS. So encrypted DNS was strongly opposed by ISP at the beginning. However, as the support for encrypted DNS grew, ISP also began to support it. On the government side, with the gradual increase of network attacks on DNS, government organizations such as the United States and the European Union have paid more and more attention to recursive DNS security and have built their own protective DNS, including support for encrypted DNS. Finally, let's make a summary. From the perspective of technical implementation, due to the wide application of HTTPS and TLS technologies, DOH, and DOT have become the mainstream application protocols. HTTP DNS was firstly proposed by Tencent and not promoted as an international standard, so it is only widely used in China. Due to the rise of big protocol, DOH has developed rapidly. From the perspective of product usage, encrypted DNS requires users to actively change the default configuration, and most ISPs haven't widely used it. So there's still a big gap between the number of applications of DFL 3. From the perspective of organization support, considering the benefits and the cost, technology enterprises are actively driving. ISPs are passively following, and government organizations are still cautious in the application due to the security and regulation problems brought by the encrypted DNS. Okay, that's all. Thanks for listening. Welcome to scan the QR code and my WeChat for more communication.
You, do we have any? Oh, we have one question from on site.
How to promote the healthy development of encrypted DNS?
Okay, as I said before, encrypted DNS bring both safety and challenges. The application of encrypted DNS involves multiple roles, including governments, ISPs, tech companies, and users in order to promote its healthy and sustainable development. It is necessary to meet the needs of government, regulation, tech company innovation, and user resolution security at the same time, and efforts should be made in policy, technology, and standard aspects.
Okay, thank you. That is from Ms. Ma. Due to the time limit, we need to move on to the next speaker. And if you have any questions, you may email our presenters. And next we have Mr. Yunyi Zhang, PhD student in joint programs of Tsinghua University and National University of Defense Technology. His talk today is about revisiting flaws of classic and modern DNS operations.
Okay. Hello everyone. I'm Yun Zhang, a PhD student from Tsinghua University. Today, I'm honored to be here to present our research. The title of my presentation is Revisiting Flaws of Classic and Modern DNS Operations. As the title suggests, my talk will cover two main parts. The first part, we divide into classical resource records in DNS, known as DNS glue records. Our research has revealed that nearly 1/4 of the glue records in the TLD zoom file are stale and potentially exploitable by attacks. Next, I will introduce our measurement work on encrypted DNS. We have discovered that the reachability of the DOE service is significantly impaired in some regions. Okay, the DNS is like the telephone book of the internet, helping users to get the IP address behind a domain name. Practically, the DNS is a top-down hierarchical structure. Parent zone maintains all delegation records for their child zone. Here the figure displays the process of the domain name resolution. If a client wants to find an address of the domain name, it must initial query that travels the top-down hierarchy to finally to get to the name server of the target domain to obtain the IP address. In terms of the process, the root server and the TLD server act like the telephone center, guiding user to the actual name server of the packed domain name to get the final IP address. To ensure the normal and efficient operation of the domain name resolution, there is a special type of the resource record in the TLD name server called the glue record. This record was first introduced the FC 1034. We can think the glue record is a phone number saved as by the telephone center. If there is an error, the user may be misdirected a wrong address, like for example, a wrong name server controlled by the attacker. In this study, we contacted the first statistical analyze of the security of the glue record. To conduct a comprehensive evaluation of glue record, we collected Zone 5 for over 1,000 TLDs, including the .com and .net. Then we categorize the glue record into 3 types: the corrective, abundant, and the stales. Our evaluation reveals that nearly 1/4 of the glue record are stale. And the right figure displays the change in IP address of the stale glue record. The left is the latest IP address, and the right is the latest IP address. The migration of the IP product providers implies that glue IP left in the Zone 5 had been forgotten. Besides, we then test the behavior of the mainstream or DNS resolve software in using glue record. Our finding reveals that all DNS software catch and use glue record without any validation, and some software misplaced trust for unvalidated glue record, including Banana and Microsoft DNS. Based on our finding, we propose a new threat model called CAICT. The core of the attack is the improperly measured stale glue record coupled with the lack of usage restriction enable a new vector for mass domain name hijacking. Here we display the process of the attacker. The attacker can find the exploitable stale glue record from the TLD file, and they then inject it to the tagged resolver, and then finally they can exploit the stale glue record to hack in the target domain names. Our evaluation reveals the concerning situation. Among over 1,000 TLDs, there are over 180,000 exploited this stale glue record, and then finally, furthermore, we identified 6 million affected domains. Of this, over 5 million domain names are active. The following figure shows the ranking of the discovered stale glue records, their TLD distribution, and the SLD distribution of the affected domain names. In the previous section, we conducted an analysis of the classical operation of DNS and uncovered new threats. Now let's move on to our measurement work on new operations of DNS, encrypted DNS. As we all know, the initial plaintext design of DNS makes it vulnerable to privacy and security threats. To mitigate these issues, the IETF community standardized for encrypted DNS protocol, DNS over TLS, DNS over HTTPS, and DNS over QUIC, and DNS over HTTP3. Collectively, we refer to them as DNS over encryption. Currently, many DNS provider clients and operating system have already supported DOE. Reachability is the basic connection for client to obtain DOE service. However, it is not simple to obtain DOE service. On the one hand, the DOE communication is complex, and on the other hand, some ISPs have blocked DOE's query to maintain their grip on internet governance. Overall, our measurement encompasses 8 types of encrypted DNS service and 7 types of the blocking detection. In addition, our measurement nodes are distributed in 102 countries or regions. In the end, we executed more than 10 million DOE queries in 2 months. Finally, based on the above efforts, we can describe the landscape of global DOE service reachability. We find that DOE service are poorly reachability in some regions. In country or regions with strict internet control, DOE blocking usually occur during TCP connection. In addition, the reachability of DOE service on IPv6 is better. Moreover, we observe that changing the DOE service type and mitigating DOE blocking. Oh, that's all. Thanks for listening.
Okay, thank you. Any questions? Oh, we have one on site.
Thank you for presentation. I'm interested in the strikes happened in the glue records, and my question is, how about the deployment of the mitigation after your disclosure about the cache shadowing attack? Thanks.
Yeah, we have disclosed the SEO to the providers and the TLD registry, and they have acknowledged the SEO, and the Microsoft DNS will release the patch in this month. Thank you.
Okay, thank you. That was from Mr. Yunyi Zhang. And finally, our last speaker will be Ms. Mingxuan Liu, Assistant Researcher at Zhongguancun Laboratory. Her talk today looks very eye-catching, a data-driven analysis of domain name abuse, ChatGPT scam, and protections.
Okay, good afternoon, everyone. I'm Mingxuan from Zhongguancun Lab. Today, I'll introduce our research results in data-driven analysis of domain abuse. First, the domain name system plays a vital role in the internet. Most of the network access in daily life starts with the domain name resolution, such as browsing a web page. But in fact, because of the universality of domain name applications, that it has been widely abused by attackers in various network attacks, such as spreading malwares. According to a Cisco report, more than 91% of network attacks start with malicious domain resolution. Driven by huge profits, attackers continue to develop various domain name infrastructure abuse technologies. First, they may use squatting technique to register phishing domains to theft the user's credentials. Second, use or attack each component in the domain name resolution process, such as launching DDoS attacks on recursive resolvers, launching domain hijacking attacks. And finally, some domain names will be abused to spread illegal content, such as illicit online gambling or drug sellings. Then we introduce our work on domain name abuse detection based on passive DNS for ChatGPT-related scam domain names. It's well known that ChatGPT, a large model-driven intelligent chat system, has sparked considerable disclosures. Its advent significantly refines machine comprehensions of language inputs, making automatically understanding natural language feasible. ChatGPT has also significantly influenced cybersecurity, and powerful learning capabilities can help solve some security problems such as phishing detections. However, the impact of LLM like ChatGPT acts as a double-edged sword in cybersecurity. There also have lots of unexpected risks of ChatGPT in cybersecurity. On one hand, the advanced abilities of ChatGPT have also been exploited by miscreants, and attackers may also train their own ChatGPT for malicious purpose, such as some fraud GPT. And on the other hand, the significant traffic generated by ChatGPT are widely utilized by some scams. Like this example, attackers use a similar domain name of ChatGPT for some malicious activities like phishing. Using the hot topic of ChatGPT, they can attract lots of illicit traffic for profit. In order to fully understanding the impact of ChatGPT on domain name abuse, we utilize the passive DNS dataset, which could provide a comprehensive view of DNS resolution. Based on related keywords and their squatting variants, we collected ChatGPT-related squatting domains in passive DNS. From the DNS resolution standpoint, and ChatGPT has led to a quick rise in ChatGPT-related squatting domains. In total, we identified over 9.3 million ChatGPT-related squatting domains. We found a strong correlation between the visit trends of ChatGPT-related squatting domains and official sites, and the updates and the major events of ChatGPT. As of September 2023, the growth rate continues to increase, showing that ChatGPT has a lasting effect on squatting domain registrations. And ChatGPT-related squatting domains use ChatGPT keywords to effectively draw in user visits, with over 31,000 domains receiving more than 1,000 DNS requests. And for example, we found an official domain, an unofficial domain, the b.ai, that offers chat features similar to ChatGPT with 200 subdomains. This domain not only got nearly 3,000 DNS queries, but also secured a domain rank in the top 100,000. After digging into their web content, we discovered that the significant traffic instigated by ChatGPT has also become a tool for luring users to gambling or porn activities. We speculate that there are two primary reasons why these underground industries embed ChatGPT-related keywords. On one hand, leveraging the popularity of ChatGPT may increase the visibility of these illicit websites to users, such as enhancing their rankings in search engines. And on the other hand, by configuring long subdomains and constructing level squatting techniques, they can deceive users into clicking them on these links on the mobile. Beyond traditional underground activities, the use of ChatGPT has led to a new security issue, the creation of unauthorized mirror websites of ChatGPT. In this work, we define squatting domains embedding ChatGPT-related keywords designed to deceive users into perceiving their chat services as officially ChatGPT for profit, as unauthorized mirror websites. More seriously, 33 phishing websites were found in our work, exhibiting the similar appearance of the official ones. In summary, our work examines ChatGPT-related squatting domains. First, we design and implement an identification method, and from the perspective of the historical DNS resolutions, we concluded the first comprehensive analysis of the ChatGPT-related squatting domains, especially for their abuse activities. Then we will introduce the second abuse-related work, which is the measurement of protective DNS services, which is a new mechanism to detect and combat domain name abuse, such as the ChatGPT-related scam domains. To block resolutions of abused malicious domains, security community proposed a new method, namely protective DNS. Protective DNS is deployed on recursive resolvers. which can proactively intercept and block malicious activities during the domain resolution process. Specifically, when a protective DNS server receives a query for domain name that appear on its block lists, it prevents access by rewriting the DNS response to return secure results, such as resolving to reserved IP addresses such as 0.0.0.0, like the example of a secure DNS vendors here. Despite the enthusiasm for PDNs, little is known about this actual deployment and the security status. In this work, we fill this research gap by presenting the first large-scale measurement study for passive protective DNS. First, we design and implement the active identification method for it. And based on these identified resolvers, we expose 3 new security risks arising from flaws in blocking policy implementations. Based on observations from empirical study, we design a 3-step methodology that actively scanning PDNs resolvers over open DNS resolvers. By actively initiating DNS requests to the collected list of generally malicious domain names and comparing the authoritative request results, the protective DNS servers can be confirmed. By intersecting the results from 6 active scanning results, we identified over 17,000 protective DNS resolvers in the world, and these identified resolvers are widely dispersed throughout 117 countries. Our empirical study on these protective DNS resolvers in the world uncovers 3 security risks arising from flow blocking strategy implementations. First is the denial of response DOR threat. We found that about 800 protective DNS servers employ no data to block malicious domain resolutions. However, this aggressive no data approach can inadvertently impact normal domain resolution. Specifically, after querying multiple malicious domains, we found that 28 protective DNS servers temporarily block all domain resolutions for the client, even those legitimated ones. We term these security risks as denial of response DOR introduced by protective DNS. Considering the threat model of DOR, attackers can exploit these security issues to deny DNS resolution services for arbitrary victims by spoofing the source IP addresses. After evaluation, we found that 7 well-known PDNS resolvers were at risks of DOR. As covered before, secure IP addresses are the prevalent rewriting policy for protective DNS. However, not in use secure IPs may be vulnerable due to the risks of dangling records, namely DAR. And beyond the exploitable security vulnerabilities, we expose 2 subversions of protective DNS due to the inadequate implementations, potentially crashing its protective efficacy. In conclusion, we design and implement the first identification method for protective DNS resolvers. According to identified protective DNS resolvers in the world, we first discovered 3 security risks arising from a flawed blocking strategy implementations. Thanks for listening.
Okay, thank you. Any questions? So do we have any feedback after you disclosed the vulnerabilities of the protective DNS?
Yeah, we received the feedback from the well-known ones, but I cannot determine which company they belong to. We didn't receive some feedback. We just disclose it from the National Vulnerability Management Platform. Yeah.
Okay, so are we continuously perform scanning of these DNS resolvers?
Yes, but
Have we seen any changes in the numbers or
yes,
the scale of vulnerabilities?
yes, the scope change may be the future work of the productive DNS deployment. Thank you.
Okay, thank you. So I think that's all we have for today. A quick recap of this session. We've talked about evolving operations, abuse, and security of the DNS, and our speakers covered issues around public suffix lists, DNS error reporting, encrypted DNS, glue records, and ChatGPT related abuse. So I hope there have been your inspiring moments. And finally, before we go, a big thank you to our speakers, organizers, supporters, and everybody joining us today, whether on-site or remote. So until next time, take care, everyone.